Okay, we're recording.
I have to tell you, that's my dog in the background. Okay.
All right.
So I I care a lot about this topic. For those who are paying any attention to us, they'll know that the last two per energy webinars were about a very similar topic. We were studying VPPs and polydynamic pricing. We compared them, but this is three in a row. We may even have a fourth if I feel like we really haven't gone very far down the road. We at first 2 weeks ago we talked about a overview, and then we last 2 weeks ago, 4 weeks ago we had an overview. Then we had a very prominent person from Lawrence Berkeley Labs. Remember his name? He was here last week, 2 weeks ago, and he talked about
Yes.
value dynamic prices, and he actually was involved at Berkeley.
Bruce Nordman, I believe.
Yeah, Bruce Norman. He actually created a technology which can become a standard for any hardware that could be remotely controlled or even controlled in response to prices. And he thought that very successful. There's also been a track record of successes in this kind of stuff in Australia and a few other places. But there still is a hardcore approach to VPPs that I don't think we are getting to the heart of what's wrong with it. That's why I think this might be the right question. So let me go to the next slide to give you an overview of the why. So here's the agenda for tonight. I'll actually cover 5 things, and this is not a lot to cover, but it's good. I'll try to go slowly down this road. So number one, we have an urgent need to optimally coax DER use. What I mean by that is distributed energy resources are needed for the grid. Why do we need them? And we have an urgent need for them. That's number one. Number two, VPPs and HDRs are virtual peaking plants and highly dynamic prices provide a way to coax DER. But what's better? That's what we're going to be talking about. And then I posed an interesting question that seems completely out of left field. Can natural evolution guide grid change? And I'm going to use my expertise that I learned in graduate school at Berkeley when I was studying mathematics. I had a thesis advisor named Hans Bremermann, who had his own brand of mathematical biology, and he was using it to not only solve biological problems, but also math problems, which is kind of interesting that it's bidirectional research. Namely, you improve math while you're studying biology, and you improve biology while you're studying math. Number four, there is kind of a assertion that I think is real, that prosumers decrease entropy, and is that okay? And that actually is kind of contradictory to number three, because biological systems always increase entropy. And number five, since survival selects successful evolution, should we only consider a grid that is increasingly resilient? And that's kind of mixing two things together, and I'll explain how that's interrelated. I think that's enough to talk about in an hour. I think you'll find it very interesting. So let's go take the next thing on actually, the next thing is to look at this from a point of view of my thesis work. So my thesis advisor, Hans Bremermann, actually used and studied and taught mathematical biology. And for most people who don't know that term, you would naturally confuse it with biomathematics, which at the time meant applying mathematics to solve biological problems. They're almost always biommathematics was using statistics to solve and predict biological problems. Statistics and mathematics may seem the same to people who are not a student of either, but they're quite different. Whereas statistics makes um, assertions couched in probability, and both from the point of view where the data comes from, and both from the point of view of what they propose. Whereas mathematicians don't approach problems that way. They try to approach problems where they can really understand things and predict without doing it in a statistical way. So that's a very big difference between a mathematician studying solving biological problems. So that's enough reason to distinguish mathematical biology from
Sure.
biomathematics.
And,
But if you
and
look at
this be
Wikipedia, you'll find
applied mathematicians then, right?
that's a really good point. And you would think it means only applied mathematicians can do either mathematical biology or biomathematics. But in fact, I have a PhD from Berkeley and I never studied applied math. And my math was always about solving a biological problem, and I did not use statistics to do it.
Hmm.
So, and since I didn't use statistics, I was pretty lame as an applied mathematician. But nevertheless, my work was applied mathematics in a very special way. But I wasn't a student of applied math. So those are kind of confusing assertions, which will get us way off on a tangent, not what I want to talk about. But one of the things I found really important, which I like to highlight in this thing, is and conversely. I'm trying to highlight instead of go back. Okay, so I'll read it to you. So mathematical biology applies mathematics to better understand and predict biology. And conversely, what does and conversely mean? It means that we learn more about mathematics by studying biology, which is a very weird idea. Mathematics seem to be significantly disassociated with the real world. But in this case, our mathematics gets better when we model it from biological problems, which is a very interesting phenomenon. And I actually observed it. In fact, I'm going to use the observation of that particular case in this particular talk, and I'll explain that. And that is to say, is that a hint about what to do? Namely, are we going to use the tools of mathematics that we learned from biology to solve biological problems? And the answer is that's exactly what I want to do in this talk. So I'm sure that piques your interest, and I didn't explain it, but that's okay. It will develop, you'll understand it. So hopefully the words aren't too small. So, okay, as I said at the beginning, this is going to be the first slide. So we have urgent need to optimally code CRUs. And if you want to, you can read this. I'm not going to. I think that's a better way to give a talk. So it turns out in order for a grid to stay balanced, to keep running, it needs its frequency and its voltage in a narrow band. If the voltage goes too high, like it goes, say, shooting for 115 volts. If it goes to 130 volts, that's too high. Maybe even 122 volts is too high. I'm not the electrical engineer to tell you what's too high. But I do know that equipment that we use really wants to see voltages within a narrow range and frequencies in a narrow range. In fact, there are electric motors that don't even have the extra valves or switches in them to run at certain speeds. They run at a certain speed because they're designed to, and they depend upon the frequency of the voltage coming, the energy coming in to determine the revolutions per second. Unlike other motors, you have to add that on to control the speed. Okay, so anyway, we have devices like those motors and many other things. Our light bulbs, for example, cannot work very well if the frequency is too high or if the voltage is too low. And many other things like air conditioners are even more sensitive. So we need these things kept in a narrow range. But it turns out if you're trying to keep it at one range and the demand exceeds supply, then the voltage and frequency will drop. Similarly, if the supply exceeds the demand, the voltage and frequency will rise. And if it gets too far out of this range, it'll cause a grid failure. So what do you do to solve the problem? Well, in the old grid, we have peaking plants, which is plants that you can throttle. You can increase the output or decrease the output. And they were rotating machines, namely, they had a rotational inertia in them so that if their rotational inertia, as well as the larger plants that weren't easily peaked, like coal plants and nuclear plants, they all have turbines. And when these turbines rotate, there's a lot of literally mechanical energy of rotation. So if the frequency goes out anywhere in the grid, that large rotating object will help to absorb and keep the frequency more stable because all that material has to change speed in order to accommodate a change in frequency up or down or changing voltage up or down. So that mechanical inertia helps keep the grid stable. But as we go to a more DER use, which means distributed energy resources like solar and wind and other things like electric vehicles and batteries, even flexible loads, all of these things can change the amount of demand or supply. And when that happens, if our grid becomes dominated by distributed energy resources versus traditional rotating inertia, then we won't have the rotating inertia to provide us the inertia to keep our grid stable. And we need other things to keep the grid stable that can rapidly be stepped up or stepped down to make sure demand and supply are kept in narrow range. And this doesn't matter which side of the meter it's on. It's either the utility might have solar plants or wind plants or batteries, and they contribute to balancing the grid. But that also happens on the consumer side. And we're talking mostly about the consumer side now as to what we're talking about doing optimally folks DRUs. So customers can have DERs that are not just energy producers, they can be demand reducers, can change their demand or increase their demand with flexible loads. And I argue that flexible loads can actually be more energy effective in terms of lowering carbon footprint than even energy efficiency in certain cases. And so we need to approach and use them with great care and love so we get the most out of our DERs, and those should be considered DERs as well. So if you have a need to use DERs, how do we use them? So the way that people have proposed, and there's a growing percentage, I don't know what that percentage is, 5%, 3%, 20%, 1%. I don't know the percent, excuse me for not knowing. But I know a growing percentage of utilities and utility districts are moving into the VPP world, which is virtual peaking plant. So what is the virtual peaking plant? So the definition of the first line is pretty much what was on the Department of Energy site about a year ago. I don't know what's happened with Trump screwing things up. It may not be there anymore. But anyway, virtual peaking plant is an aggregation of DERs that can have balanced supply and demand or quite the opposite. So what do I mean by that? Does the aggregation have to be centrally controlled? No. Does it have to be controlled by one person? All of these peaking plants sort of be a cacophony of things working together, sometimes in harmony and sometimes not. That's also a virtual peaking plant. The more it works in harmony and more it works as an aggregated unit, the more it seems like a virtual peaking plant. The reason why it's called a virtual peaking plant versus a peaking plant is because it doesn't increase supply, it decreases demand. And since you're trying to match supply to demand, if you decrease demand to meet supply, that is equivalent to increasing supply to meet demand. So that's why it's called a virtual peaking plant. All right. However, it turns out that virtual peaking plants have been dominated or are about to be dominated by centrally orchestrated DERs, VPPs. So I don't know if I can highlight on the screen. If I try to highlight on the screen, it's going to push me onto another slide.
No, it's okay. Yeah, I'm able to see your cursor.
Okay, so
yeah, so I already see it.
Centrally orchestrated are becoming the dominant VPPs. In fact, in New Orleans, the VPP that was considered most important and won, quote unquote, the prize of getting $30 million to put batteries in thousands of homes and offices in New Orleans was a centrally orchestrated VPP, pretty much a demand response VPP that the utility already had going, and then we're going to add on these extra assets. But there's a company called Energy Hub, which we talked about in previous meetings, last few meetings, which actually has a very large footprint, maybe a couple of gigabytes, watts of VPP under its belt. They're not all in one place, but aggregated over millions of customers, I guess. They're able to orchestrate that much. And one utility might have an entire 200 megawatts, I should say, of VPP under the finger of a grid operator. just like the grid operator will say, hey, we don't have enough power, bring a real peaking plant on board. Okay, they can equivalently, with Energy Hub software and assets, decrease demand in an orchestrated way. And that's really valuable. And the utility is really up on it because it's the way they like to function. Okay. However, that's not the only way to do it. In fact, one of the leaders in the electricity brain trust, a guy named Ahmed Farouki, studied about hundreds of time of use pricing situations and he showed that it consistently proved that they can be deployed to get much more of the same effect. Namely, you could get customers to respond to price, even simple prices, where the price changes from, say, 5 cents a kilowatt hour to 15 cents a kilowatt hour, predictably every day, the same 3 hours. And that generated an economic effect comparable to the VPP without anyone having orchestrated control over the devices. Okay, and that is a big deal. And so, and they even found that if the more the prices were dynamic, the more dynamic the prices, and the greater the price swings, the more success. So you might think, oh, we can only get this if we only change the price one or two times a day, or only hourly, or only 3 hours at a time pricing. But in fact, as the number of price changes increased, and the difference in the price swings increased, they got more success. If there was more fear about, because it wasn't the standard fixed cost pricing, so it took people time to get used to it, but they did, and by and large, they were successful. So Bruce Norman, who spoke 2 weeks ago in this forum, pointed out that he actually promotes 5-minute pricing as well. So those are the two ways. Which way is better? That's what we're going to be talking about tonight. So, all right. So now I'm going to ask a provocative question, which seems completely off the wall. Can natural evolution guide grid change? I don't see why anyone who's been a regular at pro-energy meetings or even regular at electricity brain trust meetings are ready for that question. And I can understand why. It's just completely weird. But I'm going to explain to you how it makes sense. So it turns out my thesis advisor, Hans Bremermann, studied the motion of a one-cell organism that could move, a mobile one-cell organism, maybe E. coli is like that. I don't know. I don't know biology enough to tell you which one it is. Maybe it's salmonella. I don't care. It's one of those organisms. And you can see I just typed this up rapidly. I made a typo. Anyway, it rapidly must find the optimal location to eat sugar. So if the sugar concentration is too low, it won't live there. It needs to move on. But this organism only has a very few choices. First of all, it only has one sensor of sugar concentration on its body, not two. So consequently, it can't know by sitting still which way the sugar concentration increases because they only have one sensor. You might notice the sugar concentration is decreasing, as you would expect, because it's eating sugar, but it would not know which way to go to get better sugar. So what does it do? Well, what it does, we can surmise that it knows why it's doing it, but it could just be doing it genetically. It moves around. It only has two choices. It can go in a straight line or tumble. And although tumbling is three-dimensional, it can tumble in any new direction. For the sake of simplicity in conversation, we'll assume the tumble is in 2 dimensions. So it can go, it might have been going north, then it tumbles and it starts going east, then it tumbles again and starts going south, tumbles again and goes north again, or any other point in the compass in a circle. That's what we mean by tumbling. So it'll go in a straight line until it notices an insufficient amount of sugar or a drop in sugar concentration, then it tumbles. And then it does this again, assuming we think by watching it that it is finding less sugar and therefore it tumbles more. And as long as it's finding sugar, it keeps going in a straight line. And that's the only kind of motion we observe. And we ask the question, with that simple of an optimization program, can it find a local or a global maximum? And in fact, he was able to model with mathematics that motion and showed not only did it find local maximums, it found global maximums, and it found it with less computational activity than you could bring in if you brought in a very complicated tool that sensed everything on the screen and calculated derivatives and figured out motions and velocities to reach the maximum sugar concentration. The maximum sugar concentration was obtained relatively soon with much fewer complications. And this model he showed was a good, if not excellent, model of the motion of the organism. So when a motion is studied like this, movement toward an increased chemical situation, that's called chemotaxis. So Hans Bremermann found a simple mathematical model with a single random step and allowed him to predict success with very few calculations and only one sugar concentration sensor. That's very interesting, but what comes after that is even more interesting. He showed that the same math model can explain evolution. So let's think about what that means. Let's suppose that you are an organism and you are going fine, you're doing fine, and all of a sudden the environment changes. It's too cold, it's too hot, it's too dry, there's too many other eaters, trees fall down or whatever. All that, any kind of change in the environment could stimulate some death. And some of your population dies, and some of strictly by random, by evolution, gets a new tool. They can see better, they can eat better, they can run faster, they can jump higher, whatever it is. And so you're traveling in a straight line and you don't tumble unless something happens forcing you to. And what happens that forces you to tumble is that you're no longer a good match for the environment. And when you tumble, you don't know where your next population is going to be like. You'll have some organisms that have, can jump higher and some can't. And the whole population moves with the average population characteristics. And if they don't move, they die. And some populations can continue for a long time without any environmental stress. And he found that the same model that he used to model chemotaxis and model evolution. But then he asked another question. If this model was so good at solving an optimization problem, which is a very simple optimization problem, what if you took an optimization problem in economics and you say, okay, I don't know what to buy or when to buy, okay? And I don't know what to buy or when to buy, and the price is going to change, and therefore you don't know what to do it. So you think if you had a complete description of the current situation and probable future situations, you could do a lot of mathematics and draw lines and do calculations and lots of calculus and so forth. But he found that this solution found global maximums faster than any other calculation method he found. And he showed it by doing a deep analysis of various models. And so in that way, the biology informed the mathematics. Do you understand what I said, Brendan? You're probably
Biology informed the mathematics.
Because what happened is when he made a math model to model chemotaxis, he found it also modeled evolution. And then when he looked at that model to do a global optimization problem of what's the highest value on a plane of a continuous function or a high derivative function, whatever, he found that method found the global maximum faster than using higher order calculation techniques.
Wow.
So the biology solving the problem, the biological problem, informed the mathematics world about how to solve more generalized optimization problems. Because in the real world, you do not know the characteristics of your curve. You don't know how many derivatives they have. You don't know the great probability of a very large difference between the point where you are and where you're going, or how it's spatially dependent, which direction to go is better. You don't know anything like that.
Yeah, I guess he worked with early supercomputers, and his work identified fundamental physical limitations on computation, and it linked energy consumption to the process of information in both machines and living organisms.
Right. You're reading the something about his work, yes. And he found that the biology informed the mathematics. But I propose to use the same model to figure out how to go from the old grid to the new grid. Why? Because, my gosh, this is a fantastic model.
Sure.
Okay, so let's try that. So go to the next slide. So here is an interesting question. Prosumers decrease entropy. Is that okay? So I think
By the way,
Brendan,
why is it? Do you think it was just a semantic issue that Bruce Nordman suggested not using prosumers but just use customers? I don't know
well,
if you.
I don't really particularly care about that terminology. I mean, I think what he was saying is if we talk too much about the fact that they make electricity, we degrade the fact that consumers can do a lot of things to encourage DERs without ever producing electricity or without ever
Yeah.
storing electricity and reselling it. Okay. So
Okay.
if prosumer understates the transition from where we were to where we're going to be. I think
Mhm.
that's what we're talking about. But nevertheless, a prosumer at least is a producer of electricity sometime. And when you produce electricity, you actually decrease entropy. And that's actually a real challenge if we're trying to model change in the grid and we observe that one of the key things in our new type of customers is that they decrease entropy because biological systems always increase entropy. So, Brendan, you know what I'm talking about with entropy?
Sure. I mean, entropy being what when the energy dissipates,
Right.
in the universe
Entropy,
at least across.
entropy measures the orderliness of your energy. So, like if you had a stack of um, sugar molecules and they're all lined up in a lattice and they formed a crystal, that would be an extremely high entropy condition. Okay. I
Oh, I was
mean,
thinking as the loss of information.
no, well, yeah, yeah, lots of information. So when you eat something like a biscuit or a piece of sugar, you break down the sugar into its component pieces and get ATP with it or something like that. And you
Sure.
do all the things you need to do, which I've listed here: grow, move, find food, procreate, etc. And but when you do that, you increase entropy. So the energy from the sun has like maximum entropy. It has, I mean, it has tremendous order in it. When you absorb it, you make sugar in your chloroplasts, and then the sugar goes into your mitochondria and so forth, going from plant to animal, etc. And each step you increase entropy in order to grow. So biological systems increase entropy. So you would think that
So, so is entropy, when you're saying increase entropy, do you mean evolving towards that state of inert uniformity? Or when you say increase entropy, do you mean it hastens the process of that kind of
well,
inert?
I've got to pull out the term actual definition. As I recall,
Yeah.
entropy is the amount of orderliness.
Yeah, a measure of the disorder randomness of a closed system is
Right.
one of the
So
definitions.
entropy is
There's
a
a
measure.
bunch. Physics and
Right.
yeah.
So when we eat, we increase entropy because
Hmm.
we increase randomness. Okay. But when we take low carbon electricity and we push it into a grid, we actually do just the opposite. We increase the orderliness of the grid. We we make the grid more energy efficient because our kilowatt hours that we add to the grid have lower carbon footprint. They're more efficient. Okay.
Hmm.
So it seems like prosumers are acting in the opposite way than a biological system would work. You follow what I'm saying?
Yeah, sure.
Okay. So um so it sounds like what we're saying is that it's hopeless to think that a grid could be modeled on a biological system because these energy moves in opposite directions in the grid. And the most effective DER users, the prosumers. Okay. But that's where we are. We're prosumers. I mean, some of us aren't prosumers. Some of us don't have solar panels and some of us don't have batteries. But I think we will all eventually, or most of us will have batteries, and many of us, or majority of us, will have solar panels. And so
Mm.
we will be putting low carbon electricity into the grid. And when we do that, we radically transform the grid. Okay. So what does this mean? How does this turn into a calculation of how to figure it out? So I have to admit, I haven't fully thought this out. So excuse me, I'm going to try to do this off the cuff. But it seems like if you have rooftop solar, you've got a very efficient system, but there's something less efficient about it because it has to be on your roof. Why does it have to be on your roof? Why couldn't it just be on your neighbor's roof? It seems like that would be more, not only more equitable, but be more efficient because, well, I'll explain why. Suppose you have rooftop solar on your roof and you've decided to spend $10,000 to fit your home's needs. However, your home's needs change, both even if your number of people in your home doesn't change, it gets colder and hotter, and so the number of kilowatt hours you need between the hot and cold time drastically decreases, assuming the main energy use in your home is heating and cooling. So during the off time, spring and summer, spring and fall, like it is now, or at least it's going to be for most people, going to be spring, your energy use goes down, but your amount of solar panels, solar energy you collect doesn't have anything to do with how much energy you need. It's how much solar energy you get. And so you're getting maybe 2/3 the maximum you're going to get in the spring than you would get in the summer. But your need for energy is 1/4 or 1/10 what it is in the summer or the winter. And so therefore, your need for electricity is highly variable. So in a net metering world, you'd have to store the energy for the future, but it's better for the energy to be used when it's generated. So with the community solar situation, you can spread that energy out to your neighbors who don't have solar. So your investment helps your neighbors and then encourages them to contribute to the world of success. And it's a cooperative function. So if the price of electricity decreases because you put solar energy into the grid, then there is an interplay, an economic interplay that contributes to the well-being of everyone. And the question is that can happen better with a VPP or than with a dynamic prices? Well, see, I don't see the grid operator communicating at the granularity of the interaction between two customers who live next to each other on the same block in some rural or urban area. However, if we had micro pricing, which is what is promoted by Kay Aiken, where the prices are not just decided by the wholesale marketplace, but they're decided on the feeder that you're on. So if there was a fluctuation of demand in a nearby house, then the electricity at one house could be priced according to what's going on in that feeder. And then you get a micro response. And that response could be like the salmonella. It's not satisfactory, so it tumbles because there is a local action that causes a response. Okay, a similar thing would happen with electric vehicles. If you have electric vehicles, and I mean, I love mine because it has virtually no reliability problems, no repair problems. The energy is available, and but when I could actually use my electric vehicle to go get electricity 4 miles away or 10 miles away, start up in my car and use it to recharge my house. And so I can get electricity from somewhere else and help contribute to the stabilization of the grid. But also, electric vehicles can be charged when we otherwise don't need the electricity because it's the middle of the night. So most low carbon electricity is available at the same time the electric vehicle's there and parked ready to absorb it. And so it helps stabilize the grid and decreases the great fluctuations of electric prices. But this is a local phenomenon and it has to be encouraged by prices. I can't see how it makes sense for a VPP to charge everybody's electric vehicle at the same time. It's just not right. You'd want to charge it when the price is low, and it could be that one guy's use would raise the price for someone else. So anyway, I don't know if that was coherent. I was trying to be. So let me go to the last slide. So since survival selects successful evolution, should we only consider a grid that is increasingly resilient? So let me unpack what I just said. So what do we mean by survival selects successful evolution? Well, go back to the Darwinian concept of evolution, which says only those that live are evolving. The dead things don't matter; they're gone. So if you get a evolutionary change, which is a random change, and you die, well, that's part of the process. Okay, and we evolve by throwing away the dead stuff. So what's the dead stuff in this case? Well, is it a customer who refuses to change? Well, I don't want to kill people because they refuse to change, but I can reward people who want to change, right? And if you reward people that want to change enough, people will move toward that. And so it's implicitly the opposite of survival selects evolution. So we only consider good that's increasingly resilient. Well, so I think the easiest way to think about that is a battery. If I can buy a battery with a VPP because the VPP helps me pay for my battery, or can I buy it more easily with highly dynamic prices? I think the answer is emphatically the second one as opposed to the first. And here's why. VPPs seldom, if ever, give you a high percentage of the value they generate. It goes to the guy who owns the aggregation process. In New Orleans, that's the utility. So if there's $1 to be saved by flexing the way you use energy with either VPP or highly dynamic prices, 90 cents of that's going to the utility and only 10 cents going to the customer with the VPP. But with highly dynamic prices, it could be just the opposite. 90% goes to the customer and only 10% goes to the utility. And if you have 90% of the savings, you could easily buy a battery. Now, if you bought a battery, you could buy electricity when it's cheap and sell it back when it's high, or when it's low carbon and sell it back to the grid when the grid is otherwise loaded with high carbon electricity. So, but you've paid for the battery. And when you've paid for the battery, when the grid goes down, that battery will save your life in a power failure. Or another way to look at it, I like to think of this third bullet on my slide as the key idea. I think a necessary ingredient for success is that all off-grid homes are paid to join the grid. By so doing, decrease the cost of electricity to everyone. And I should also say increase reliability. Suppose you have an off-grid home. A off-grid home is by definition a home that can survive off-grid. Whether it's all the time or 90% of the time is sort of relevant, but not necessarily important. But usually an off-grid home has a lot more battery and solar than needed than an on-grid home because they can't depend on another resource to weather, say, a week without solar energy, which our off-grid home would suffer from that. So they would need 5 times as much battery storage as a home on-grid, which could depend on the grid to recharge the battery daily, or even a power outage for one day. They can handle that, but not for a week. So an off-grid home would usually have enough solar and batteries to go a week or even a month maybe with unfavorable solar gain. Okay, well, why would a home like that want to get on the grid? It already has all the resources it needs. It doesn't need to get on the grid and deal with all the craziness, the prices that don't work, and someone trying to control your equipment and cross subsidies, etc. Why would you want to get in that mix, which is fraught with problems? And the answer is always economic, only if it pays to do it. So if the grid is a VPP, you're not going to get paid much to be on the grid. But if it's highly dynamic prices, you get paid a lot. So you're literally paid to get on the grid. When you get on the grid, you increase the stability of the grid, the economics of the grid, and it's easier for the grid to withstand these power surges with a large cadre of off-grid homes joining the grid, but they have to be paid to do it. And you're not going to get paid to do it with the VPP. So I'll close the talk with this last line, which sounds out of context until I explain it to you. We'll go in a straight line until it's time to tumble. So what does that mean? What are we doing now? We have we have prices that are not time of use. And we have a poorly successful demand response program in New Orleans, which is trying to soup up its VPP. But its VPP is not going to get us to the resilience that we need. It's not going to cause people to do community solar or hybrid community solar. It's not going to pay for that. Okay. And which means that it's going to work for a while, and then we're going to realize it doesn't work and it's going to be time to tumble. It means we have to try something else. And we'll keep trying things and we'll have failures. We'll keep trying things and have failures. That's how things normally go in a society. But why do it with the foresight of a salmonella or an E. coli? Why not do it with the foresight of Hans Bremermann, who said this approach to modeling the world has expanded mathematics, which means we can predict. We can't predict that any particular tumble in any particular straight line action will be good, but we can be confident that this method will get us to a really good solution. Because when it's going in a straight line, it'll succeed, and when it stops succeeding, it'll tumble, and we'll find a new way on. So it's like highly dynamic prices. When do we change the price? Do we start instituting bidirectional pricing? Do we start instituting prices that are not determined by just the wholesale price, but what's going on across the street, or the way someone's using a electric vehicle? And I see that as being the future. That a grid that evolves like the E. coli moves in a search of sugar will find a better solution. And I see the highly dynamic pricing up for the task because it shares the value 90% of the value creates. And it has bidirectional pricing, and it can change prices multiple times a day and in multiple locations. It has the chops to handle the variety that might be needed. So that's my idea. I don't know how fast I did it, how much time I have, or anything else. But
Certainly.
yeah, we went 42 minutes, so it's a good time to stop and let people ask questions. So what do you think, Brendan?
Well, I think it's it's nice to uh, involve lots of different concepts like adaptation from evolution by natural selection
Right.
into these concepts. One thing that I worry about is the focus on resilience is especially important in New Orleans. But I'm wondering how much of a selling point it would be if it was, let's say, somewhere in the Midwest where it maybe isn't as big a priority, or maybe in philosophy, there's this idea of a defeater concept. So it means like maybe it just has to be good enough so that it doesn't undermine some normal condition. Um, One thing that sticks out to me is some corporations will pay the environmental fine because they'll lose more money in, let's say, in adjusting to the regulation than they would just paying the fine and continuing to produce the way they are. And so I wonder if this focus on maybe like, well, the more resilient a grid is, the more it'll be adopted is, or the more that it'll should sort of survive. Um, I did like that idea of motivating people's behavior with being paid, because I think it's a more democratic view of selecting options. But all I'm thinking of is okay. So we have evolution, right? And in the wild, it makes sense. But then in the zoo, in captivity, a lot of the things that would naturally be pushed as important don't really matter as much, right? They probably like extract the semen with the needle or something. Either way, they breed the animals, but it doesn't necessarily track any sort of survival mechanism, right? Um,
I mean, that could very well be the case. In fact,
yeah.
I was watching a series called Alone, which is on Netflix now. You can watch it now. And the one that shows is season 11, where people are thrown into uh, extreme North America near Alaska, where they're literally in the Arctic Circle and they have to survive. And whoever survives the longest gets $500,000.
Hmm.
And so there's no safety net. If you want to tap out, they'll pick you up, put you on a helicopter, and bring you to a hospital. But otherwise, you're all on your own. And so when we are inside our electric grid that we have, we are not in a wilderness.
Exactly. Yes.
And because we're not in a wilderness, we don't see the forces that force us to change. In fact, even highly dynamic prices can't be viewed as a signal that everyone should watch because we can't literally be the most anal person in the world who watches the prices every 5 minutes and turns all our light switches on and off in response. It has to be more automatic than that. But it doesn't have to be so grid controlled as the VPP does, because
Yeah.
as Bruce pointed out, he has these devices in his house that look at the predicted prices over the next 10 hours, which is all he needs for his devices to be controlled, and that gets them a lot of the money. But even more trivial kind of control mechanism worked really well. When we modeled CLEP, the predecessor name of prorate, in our CLEP dashboard in 2018 and 19, we were able to show that if you maximize the control and did everything just right on every day, you might save, say, $100. I'm using that as a
Sure.
baseline number. But if you set it to work the same way every day for a year, like you always set your water heater to charge between 2 and 4 p.m. a.m., sorry, and your air conditioner is always to run between 10 and 3 p.m. with increasing output in 2 o'clock or something, and you always ran your car so it charged at nighttime, and you always ran your solar panels and expected them to maximally charge between 10 and 3 p.m. with increasing intensity around noon, etc. You do all the things that are most likely, but you do the same thing every day. You still make $70. You make
Mm.
70% of the money you make that with no watching what's going on, except once a year, you look what happened last year and you reset all your devices to optimize what happened last year. If you did that every year, you would get 70% of the savings. Is that enough? I think it really is enough. And that will allow you to buy batteries. It would allow you to invest in more efficient air conditioning equipment or more load flexible water heaters, or decide, oh, it's time to tighten my windows, because you would see the interplay of all these choices and then change your utility bill to literally about 80% of what it would have been, assuming you don't have any money to invest. And if you have money to invest, we showed you could turn your utility bill from $1,500 a year to minus $1,500 a year. Namely, you get paid by the utility because the rate design was bidirectional. So there's a lot you can do without being an anal rate watcher. So the rates change, but your ability to perceive them can be summarized daily, weekly, or monthly, or yearly to find trends, how to do it. And so it causes people to buy equipment that is really good. But another thing about it is that someone could come along with a new widget, a new battery, a new solar collector, a new water heater, or a new something else that no one has, like a device that turns tomatoes into oranges or something, whatever it is that you might want. Okay. And that tool, you use it, and the rate design will naturally be compatible with it. And you'll be able to make a fortune. Like, suppose someone came along, I've got a new window you can put in that will collect energy in the summer, I mean, in the wintertime, and reject energy in the summertime, and it costs $1,000 to install, and I'll install it, and I'll show you it'll save all the money you spent in 1 year to do it, and you'll keep making the same kind of money every year for 10 years. That kind of thing could be invented by someone and sold in a marketplace with the prorate rate design very easily because it fits into the economic model.
Yeah,
Anyway,
I agree.
so there it is. That's what I hope to say. I don't know if I said it clearly or vaguely, you know. I wish I could show you a picture of of a video that my thesis advisor Hans made of these animals moving through the sugar concentration and show how it's sort of predicted by the mathematical model. But I can even explain the mathematics behind it if you wanted, but it's just not that complicated. Okay.
Yeah, I
Anyway,
guess it's Bremermann with two N's at the end.
yes,
Yeah.
he was from his family was from Bremer, which is a town in northern Germany. So he was from Bremer. So he was
He's
a
a
Bremer
Bremermann.
man. Okay. All right, that's I think that's how his family name came. Okay.
Yeah, my grandpa said because my last name's Moore, I'm a Moore man.
You're a Mormon, right?
I'm a Mormon.
So
Yeah,
that means that you can have three wives.
something like that.
Okay.
But yeah, either way, Bremer, Vader Bremen is a really nice southern. Uh, yeah, they have a really great German football club there.
Oh,
Vader,
really?
yeah, Bremen. I haven't visited that town. I've been to Munich and Cologne, and Dusseldorf and all those.
Uh-huh. I have a first cousin that lives in Düsseldorf.
Uh, well, I'll hit stop on the recording for the
Okay.
presentation portion. So that'll be the part
Right.
that's shared.
Okay.